That was awesome. I totally trolled all of you by putting this capacitor up here. Remember that?
Yeah.
That was cool. Sorry. I mean, you got over it. But anyways.
I'm not over it.
Still bitter.
It still hurts. Like that roller coaster problem. That was real stuff.
What? Please, I'm like 4 feet away. I can't hear.
Are test corrections available yet for this problem? Because I want to see it. Well,
The solutions are totally available.
I think she needs for our test. The one we took in class.
Oh, that's right.
Yeah, we on the back. We don't.
Yeah.
In the back. Oh, okay.
Do that after you.
Yeah, I'll post them today and then just
I'm gonna ask you that.
Wait, what did you see?
No, okay.
like a week ago or something. It's in
Oh,
there.
did they?
All right, so yeah, so for this, so first, what's the steady state current through the ammeter? That should be obvious, 0, because this path has no current. Right? And especially if it's been connected for a long time. Hopefully you realize that if you just turned on this switch, then there would be some current, yes? Right, because these capacitors are filling up. And then that current would be a function of this. Remember that? This would be a statement that would define the current if we just turned it on, like after like 1 second, 2 seconds, 3 seconds, whatever. But because they said for a long time, we don't have to worry about that. We can just say 0. Okay? So then, calculate the charge on the 10 microfarad capacitor. So that capacitor, yeah, because if we look at that capacitor, like the 2 ends are connected directly to the battery, right? Because if there's no current in the circuit, how much voltage is being used up at those resistors? 0, right? Because if current is 0, then voltage is 0 on a resistor. So then that means this is 30 volts. So if this is 30 volts, then whatever, just use C, it's Q over V, Q is CV, so blah, 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 whatever.
Oh, we have to convert it to just Faraday.
No. What's that?
We have to convert microfarad to Faraday.
Yeah, you have to take 10 microfarads, because this is 10 times 10 to the minus 6 farads. And then you multiply that by 30 volts, so you get 3 times 10 to the minus 4 or something. Okay, and then calculate the energy stored in the 5 farad capacitor. So the energy stored in the capacitor, U sub C, is 1/2 CV squared. It's a bunch of other crap too, but whatever.
What's the rest of it?
So like we know that V is Q over C. Like you can substitute this equation in to get other stuff, like as easy as possible. Like you know that's 30 volts. Well, actually, you don't have to substitute anything. This is 30 volts, so why not just use it? It's easy. Because there's 30 volts across this, right? You see that one's in parallel? So they're both 30 volts. So then that becomes 900. 900 times 5 is 4,500, and half of that's 2250. But that's 2250 microjoules. So that'd be like 2.25 millijoules or something like that. Questions?
So this is correct. So because like resistors can't actually
Yeah. Yeah, when a resistor has, well, what does Ohm's law say?
Ohm's law says that B equal by R.
So, if I is 0, V is 0. Yes. Okay, very good. Next, the switch is now closed, so we connect that, and then we let it come to a steady state, so we let it stay even, and then we calculate the steady state current through the battery. So this one is just a function of where's the current going to flow, right? It can't flow through a capacitor, so it's just going to go through the resistor. So it's a function of total resistance of 60, voltage of 30, V equals I is V over R. So Yeah, just do that. So then, the next part, calculate the final charge on the 5. Now this one right here is slightly interesting. And it's slightly interesting in that, how do I know the voltage across that capacitor? What do I use? Okay, so what 2 laws govern, well, okay, I guess there's 3, but, okay, Ohm's law, obviously, but what 2 other laws govern all of the circuits that we deal with? Kirchhoff's 2 laws, what are they? Loop rule and junction rule. What does the loop rule say about the voltage across the 5 microfarad capacitor?
It's equal to the voltage going through to 40.
Yes, this has to have the same voltage. Does that make sense? So if I just do a simple proportion, right? This one has twice the resistance of this, so this, and assuming that they both are going to have the same current, this should have twice the voltage of that. So then this is going to be 20, it's going to be 10. Does that make sense? Okay, so what I would say is, based on the loop rule, then the voltage on the capacitor will equal the voltage on the 40 ohm resistor. And then the voltage on the 40 ohm resistor is 20 volts. Because I could also say, using the loop rule in proportion. Boom. I'm going to have to use math. And then that allows me to, once I get the voltage, now I just use this again. Or sorry, this. Because I'm looking for the charge. So then I multiply 5 microfarads times 20, give me 1 times 10 to the 4th coulombs.
Can you do the math?
Sorry?
Can you do the math?
Oh, yeah, sure.
Like, I can't see it.
Okay, so I would say something. I would actually say the voltage on the capacitor will equal the voltage on the resistor. And then if you want to do it the long way, then I would say, oh, I know. I would say the voltage on the resistor is equal to the current through the resistor times the resistance of 40 ohms. So then this is going to give me 20 volts. Okay, and now I can say Q is CV. So Q is going to be C, which is 5 times 10 to the minus 6 farads times 20 volts. 5 times 20 is 100. That gives me 1 times 10 to minus 4 coulombs. Okay, questions? All right, and then finally, wow, it's only 9:35. Really?
Yeah.
What?
I never have enough time to do anything.
Only time change.
Well, Mr. McClure, maybe it's because we already
physics
seen this problem. So.
Yeah, maybe we've seen this problem, so that's why we're blazing through. Oh wait, sorry, can't say blazing anymore.
Why
Amazing.
Okay, so calculate the energy dissipated as heat in the 40 ohm resistor in 1 minute. So then the energy, so since we say power is energy over time, then energy is power times time, and power in a resistor, we know the voltage already, that's 20 volts, so I'm going to pick V squared over R, that makes life easy for me, times the time, which is 60 seconds.
You can't put.
You can put IR, you can put I squared R, you can put IV,
V times T.
can't do V times T. No, because V times T is coulombs, no, I'm sorry. It's joules per coulomb times seconds. That doesn't do anything.
You sound good.
Alright, so then V squared is 20, so that's 200 divided by 40 is 5. 5 times that's 300 joules. It's probably when you're doing the multiplication. Or it could be I'm off by 0.
I got 600 joules.
What's that?
No, it's 600 joules.
Isn't it
I got
20 volts square?
we got 20 squared.
Oh yeah, 400. 20 squared is 400. It should have been 40. Yeah, whatever. Okay, so let's see. So the answers for that is this one? No, this is the kinematics one. So just so that you can have. Okay, let's see what
You're
that
still waiting.
Here we go. Okay, so this is all, yeah, that's fine. That one's good. Yeah, the current's obvious. E. Okay, that one's fine. And then this one, I forgot to square it. I added a 10 instead of squaring it. So yeah, you should get 10 watts. And then that would give you 600. Okay? And that is it.